minutes more. Okay, it's great pleasure to have Filip Brocic from Montreal, who will be telling us about Riemannian distance and symplectic embeddings in cotangent bundle.
Yeah, thank you so much for the invitation, and it's really a pleasure to speak at the Zoominar. So, sorry, some neighbors are having some reparation of the apartment, so maybe you'll hear some noises. But okay, let me start. Okay, so I'll start with the definition, and this definition is motivated by ball packing, but relative version of ball packing. When I say relative, I mean to some Lagrangian submanifold of a given symplectic manifold. And for us, setup is given by closed, smooth and closed manifold N, and neighborhood W, which is a open bounded neighborhood inside of cotangent bundle of the zero section N. So our symplectic manifold for the whole talk is going to be a cotangent bundle. And now, given 2 points Q1 and Q2 on a zero section, I want to introduce a distance-like function, which I call rho W. And rho W of Q1 and Q2 is supremum of pi r squared over 2 over all symplectic embeddings of this joint union of two balls of equal radii. Now symplectic structure is canonical one on the cotangent bundle and the standard one on the R2N. And additionally, I have two other requirements. One is that the pre-image of the zero section is equal to disjoint union of the real parts. This is called a relative embedding to the Lagrangian, and our Lagrangian is a zero section. And additionally, I need to put an assumption on the fibers where I require that pre-image of disjoint union of the fibers is disjoint union of imaginary parts, and actually this part is going to give me distance properties. Okay, if there are no questions, I would like to give some examples to clarify this a bit more. So now I'll fix a Riemannian metric on S1, and I'll take my open neighborhood to be unit disk cotangent bundle, and then we'll see that actually in this particular simple case, this introduced distance rho W is equal to the Riemannian distance. So in this case, if we identify tangent space of S1 with S1 cross R, our Riemannian metric or norm squared of vector V inside of a fiber over Q is actually square of a positive function evaluated at the point Q times absolute value of V squared. And correspondingly, dual norm on the cotangent bundle of S1 is given by absolute value of covector P squared over square of a function. So unit disk cotangent bundle is actually set of points QP such that absolute value of P is smaller or equal than the function of F. So our unit disk cotangent bundle is actually given by a graph of a function F. And then in this figure, let's say, we want to calculate what is length of a curve going from Q1 to Q2 in this direction. So if we have some parameterized curve from Q1, Q2, and we want to calculate its length with respect to Riemannian metric G, is going to be integral from 0 to 1 of f of gamma of t times absolute value of gamma prime. And then if we put a change of variables, this is going to be integral of from Q1 to Q2 of function f, which is just half of the area of this cotangent bundle restricted to the interval Q1, Q2. So we can actually see that distance between Q1 and Q2 coincides with this area. But on the other hand, since in dimension 2, area preserving diffeomorphisms are symplectomorphisms, we can actually find two balls which really realize this particular distance. So distance rho W in this particular setting is going to coincide with the Riemannian distance. On the other hand, if we have a bit stranger and a bit unsymmetric domains W, we'll have some properties which are not this. So the triangle inequality is not going to be satisfied. So in this particular example of neighborhood W, so this is, for instance, unit disk cotangent bundle of non-reversible Finster metric, and here A denotes the area below blue region from point P to point Q. And in this particular case, from the figure, we can see that distance this symplectic distance between P and Q is going to be exactly A. And the reason is because we have more than A on the right-hand side. So if the area here was less than A, actually the distance between P and Q would be just this area, which was on the right. So because this area here gives us the obstruction because of our assumptions on the real parts and the imaginary parts of the embeddings. On the other hand, if we look at points Q and R, distance there is going to be A over 3. And similarly, distance between R and P is again here because of identification. We have the distance between P and R is also A over 3. So we see that triangle inequality is violated for this particular example. But in a way, I'll explain how we can fix that in general. So if we take some piecewise smooth curve parameterized by the interval 0, 1, using the idea from the metric geometry, I want to calculate length of this curve with respect to this symplectic distance-like function. It's not, as we saw, it's not really a distance, but still we can try to measure lengths. So length of curve gamma is supremum of sum of distances between images of consecutive points of a partition, and then we take supremum over all partitions. Okay. If that is clear, I would like to proceed with the statement. So now I want to fix a Riemannian metric on arbitrary manifold n, and I want to look at neighborhoods which are coming from the unit disk cotangent bundle. Then the statement is that length, which is calculated using the symplectic distance of a curve gamma, actually coincides with the Riemannian length. Okay. Are there any questions? Okay, if not, I would like to give some remarks. So in a way, this is very particular for the Riemannian metrics. So here I'll give two examples where distance length structure is either not continuous or not differentiable. When we have a Riemannian length, length is continuous with respect to C1 topology on the space of paths. But in these two particular examples, on the left, we can see example of a domain where length structure is not continuous with respect to C1 topology. And this we can see if we take path of paths going like this, and continuity is going to be the point of discontinuity is actually lying over this point here. On the other hand, on the right-hand side, we can see an example of a domain which is unit-disk cotangent bundle of a non-reversible Princeton metric. And here, actually, our length structure, in a way, does not care about this part here, because we need some sort of symmetry. So if this is height h, we also need the same height here. So again, if we consider some path of paths like this, and if we want to differentiate with respect to the parameter, our function is not going to be differentiable at this point, the length function. Okay. So before I continue, so in the rest, I'll like to speak about ingredients of the proof. I'll not really sketch the proof, but I'll speak about two essential ingredients. One is ingredient for the upper bound in this theorem. And this upper bound is coming from the theory of pseudo-holomorphic curves, which are their existence is obtained from Vrep-Floor cohomology. And the other part is proving the lower bound, which is given by some explicit constructions of some symplectic embeddings of balls in some local models of a cotangent bundle. So the first technical proposition which yields to the upper bound, if we start with a symplectic embedding of this joint union of two balls of radii R1 and R2 inside unit disk cotangent bundle, and if we assume that this embedding is relative to the zero section, and also if we assume this condition on the fibers, so that pre-image of this joint union of fibers over Q1 and Q2 is this joint union of corresponding imaginary parts of the ball. Then sum of pi r1 squared and pi r2 squared is bounded by 4 times the distance. And essentially the proof is contained in this picture. The only problem is to find this holomorphic object here. And also we would need to find holomorphic object such that its energy is essentially equal to the distance between Q1 and Q2. And so this perturbed holomorphic object is actually defined on a half-infinite strip. It satisfies appropriate boundary conditions on 2 fibers and on the 0 section. And at infinity, it's asymptotic to a cogeodesic. So this is actually a lift of a length minimizing geodesic between Q1 and Q2. And the existence of this object is obtained through isomorphism between Vepler cohomology of 2 fibers and the Morse theory for the space of paths with fixed 2 endpoints. Okay. Now I would like to speak a bit about the construction of the embeddings for the lower part of the inequality, of the lower bound for the equality. And for this, I want to introduce one object, which is Lagrangian B disk. This is essentially just the product of a Lagrangian n-dimensional disk in Q coordinates of radius A, and norm is given in this particular setting. It's just the Euclidean norm. And the product is with another Lagrangian n-dimensional disk in P coordinates of radius B. And now the lemma is we have a symplectic embedding from a ball of capacity 4AB. So capacity of this ball is 4AB, but radius is given by 2 times square root of AB over pi. And additionally, we have that this embedding is not only symplectic, but it also preserves a standard Liouville structure, which is for us sum of PDQ, because we want to look at this Lagrangian B disk as a local model for cotangent bundle. Okay, and now a bit about the proof. So without loss of generality, let's set A and B equal to 1. And now I want to fix a function, which is just integral from 0 to q of square root of 4 over pi minus t squared. And essentially, this function is giving us at point q the area, of this part of the circle. And if we set a function like this, I want to define a diffeomorphism sending n-dimensional disk of radius 2 over square root of pi to the unit disk. And this is defined using a radial diffeomorphism. It's sending q to f of norm of q over norm of q times q. And from the definition of a function and it follows that really the image is really contained. The image is really of norm 1, at most norm 1, and one can actually show that this is really a diffeomorphism, again, from the properties of this function f. So, and this is giving us essentially the diffeomorphism of the real parts. Now, I want to use a canonical transformation, which is a lift of diffeomorphism of the base. So I want to define an embedding as it acts on QP. So on the first coordinate, it acts as diffeomorphism phi. And on the second coordinate, it acts as a inverse of a differential transpose, which acts on the point P. And now, again, from the properties of this function, what one can show that okay, so sorry for the sound if you can hear it. So one can actually show that really the codomain, if we restrict this embedding to the ball of radius 2 over square root of pi, that the image is really contained inside of the Lagrangian B disk. This follows from the fact that the norm of differential of phi is bounded from below by f prime of q. Okay, Now I would like to speak a bit about, let me first explain maybe how this implies the lower inequality. So if we have 2 points which are very close by on our manifold N, Q1 and Q2 inside N. So then I can embed a disk in a normal neighborhood, which is of radius distance over 2. So, and essentially inside of unit disk cotangent bundle, I'll have copy of 2 disks of the form product of distance over 2 in Q coordinates times unit disk in other coordinates. And as we saw, the capacity of this object is 4 times d over 2 times 1, which is 2 times d. But then we have 2 such products of disks. So in total, we'll have that sum of capacity is 4 over d. But that's why we calculate in the definition of rho w, we had pi r squared over 2, where r was a radius of 1 ball. So we need to divide by 4, and we can actually see that in a way, lower bound is also d, but when the points are very close. In reality, we need to add some small epsilon here. We cannot, because of the curvature. So it's not really just ball of radius d over 2 times ball of radius 1. We just need to shrink a little bit, but still we obtain a lower bound for rho w, which is for points which are close by on a manifold. And then when we take, when we sum overall partition, over the partition, we actually get the inequality between length structures. Okay, now I want to speak a bit about relationship between this result and strong Viterbo conjecture. For that, I need to recall what is a normalized capacity. So we need to have conformality, which is that if we take rescaling by a factor of a of an open set, capacity of a times x is a squared of capacity times capacity of x. We have a monotonicity axiom, which states that if there is a symplectic embedding from x1 to x2, then capacity of x1 is smaller or equal than capacity of x2. And then normalization states that the capacity of unit ball and capacity of the unit cylinder is equal to pi. And the main 2 examples for us are Gromov-Vid and cylindrical capacity. And the reason is all other normalized capacities are squeezed in between Gromov-Vid and the cylindrical capacity. But the strong Viterbo conjecture states that all normalized capacities coincides on convex sets. So essentially, we need to prove that cylindrical capacity coincides with the Gromov-Vid, and with this construction of an embedding that I just presented, we get that the Gromov-Vid is bounded from below by 4 times AB for Lagrangian B disk. On the other hand, we can look at the projection on Q1 P1 plane, and we can see that the projection of a Lagrangian B disk is equal to the product of interval minus AA and interval minus BB, which is symplectomorphic to the circle of radius of area 4 times AB. So also the cylindrical capacity is bounded from above by 4 times AB, hence we get the equality. Okay, so I'm a bit short on time, so yes, maybe I'll just state the definition of relative Gromov-Vid and give as a corollary of my previous result something on the relative Gromov-Vid inside unit disk cotangent bundles. So initially, relative Gromov-Vid was defined by Barrois and Cornea for Lagrangian submanifolds inside symplectic manifolds. It's the largest capacity of a symplectic embedding of a ball inside M, such that pre-image of a Lagrangian is equal to the real part of the ball. And for our purposes, because I had this restriction on the imaginary part, I also want to introduce for disk cotangent bundles modified relative Gromov-Vid, which additionally asks that the pre-image of the fiber over a center of the ball is equal to the imaginary part. And recall that we had a proposition that pi r1 squared plus pi r2 squared was bounded by 4 times the distance. So we can take r2 to be arbitrarily small, and r1 can get at most 4 times diameter of n. So as a corollary, we get that the relative Gromov width is bounded from above by 4 times diameter. And I would also like to advertise a work which I did with Dylan Kent, but this was using different techniques. And actually, we did not have this condition on the imaginary part. So we really bounded the relative Gromov width by some quantity which is presented here. It's essentially the largest action over some non-contractible loop. And actually, this result we had is sharp for a flat tori when we consider our open neighborhood to be unit disk cotangent bundle over a tori, which is with the flat metric. So I will stop here and thank you for listening.
Thank you. Okay, well, let's thank our speaker, I guess, again, however you can do. And maybe we can have a room for one quick question, if